Here is a story that illustrates a mistake many practitioners encounter when they are new to ML ops and early in their machine learning development. I built my first serious ML project, a stock price forecasting notebook. It ran perfectly on my machine. I trained the model, compared predictions to actual prices, and proudly shared the results. However, when I packaged the project for others, my requirements file had ballooned to several hundred packages, most of them completely unrelated to the project. Anyone trying to reproduce my work hit dependency errors, version mismatches, and install times nobody wanted to wait through. The model was never the problem, the foundation was. Python setup, environment management, and project structure are often dismissed as overhead, the boring steps people rush through before the real work starts. Treating Python setup, environment management, and project structure as overhead, the boring steps to rush through before the real work begins, often leads those new to ML ops to start writing code before the necessary foundations are in place. In applied machine learning, the infrastructure is not overhead. It is the work. A model that cannot be reproduced is not a model. It is a one-time result. A model whose data pipeline is undocumented, whose pre-processing steps are buried in a notebook cell no one can find, whose dependencies shift between runs, that model is a liability waiting to surface in production. Data is the model, and the foundation that makes data trustworthy is what this video is about. The Python machine learning stack is not just a collection of libraries. It is the layer of trust that sits between raw data and a model you can actually rely on. NumPy handles the numerical arrays and vectorized operations everything else is built on. Pandas gives you the tabular data structure that most real-world data actually arrives in. Scikit-learn provides a consistent, well-documented interface for pre-processing, modeling, and evaluation. PyTorch and TensorFlow extend that into deep learning when the problem demands it. Together, these libraries make Python both accessible to beginners and powerful enough for production systems. But the stack is only as good as the discipline applied around it. Every machine learning project should begin with its own isolated virtual environment. This is not a preference, it is a structural requirement for reproducibility. A virtual environment prevents one project's dependencies from interfering with another's. It lets you pin library versions so that the experiment you ran in January can be reproduced exactly in June. It keeps your requirements file lean, listing only what the project actually uses, not everything you have ever installed on your machine. The problem that destroyed my first project's shareability, a bloated, uncurated dependency list, is entirely preventable. Set up the environment before you write a line of code. Export it only after you have pruned what does not belong. Reproducibility in machine learning goes beyond source code. It must cover data, models, and experiments, and each requires a different tool. Git tracks code and configuration files. Every commit is a snapshot, making it possible to roll back, branch, and audit what changed and when. But Git was not designed to manage large datasets or trained model weights. That is where DVC, Data Version Control, comes in. DVC extends Git to track data and model artifacts in cloud backends, so the exact dataset version that produced a given result can always be identified. On top of these two, a recommended third practice is to name experiments with programmatically generated timestamps and recording SHA-256 hashes within structured metadata files, commonly JSON, to ensure reproducibility and traceability. The timestamp tells you when. The hash tells you exactly what, because the same file, byte for byte, always produces the same hash. Together, these practices mean your results can be reproduced exactly, audited for regulatory review, and shared with collaborators who can trust what they are receiving. Before writing a single line of model code, the structure of your project sets the stage for everything that follows. The following are questions every practitioner should ask at the start. What is the purpose of this project? Is it an exploratory notebook, a deployed service, or a teaching demo? Who will use it later? How will it evolve? How will data be handled, stored, and kept compliant? How can it be scaled and deployed? A clean project structure separates data, modularized Python source files, notebooks, and results into clearly defined directories, ensuring that exploratory analysis and reusable production code live side by side but serve distinct purposes. When combined with Git and DVC, it means every component of the project, code, data, models, can evolve without chaos. The hidden cost of skipping this step is restructuring later. Broken imports, misplaced files, dependencies that no longer match. Every time scope changes midway through a poorly structured project, friction compounds. Investing in structure at the start is not overhead, it is the work. Once the directory structure exists, there is one more step before writing a single line of code, and many practitioners skip it entirely. Write a design document in plain language. Not pseudocode, not a diagram, prose. Describe what each layer of your project is responsible for, what it accepts, and what it promises to return. This is where data contracts and code contracts get defined together. What does the raw data layer guarantee to the pre-processing layer in terms of format, shape, and completeness? What does the pre-processing pipeline promise to deliver to the modeling layer? What does each function accept as input, and what is it obligated to return? These are not implementation details. They are agreements between the parts of your system, written before any part of the system exists. The payoff is coherence. When you eventually write the code, you are implementing known interfaces rather than discovering the architecture mid-build. Ambiguities surface in the design document, where they are cheap to resolve, instead of in the codebase, where they are expensive. And when you return to the project weeks later, or hand it to someone else, the design document tells them not just what the code does, but why the structure was built the way it was. This is a lesson shared here because formalizing data and code contracts before implementation transforms isolated scripts into deliberate, durable systems built on explicit agreements rather than assumptions. In practice, this discipline materially reduces development time, lowers architectural risk, and produces a codebase that is faster to implement, easier to extend, and more resilient over its life cycle. Chapter 2 of my book closes with a hands-on exercise built around the bank marketing dataset from OpenML, a real-world classification task with mixed numeric and categorical features and class imbalance. The exercise presents two approaches, and the contrast between them is the lesson. Option A is a good place to begin when learning the workflow. Load the data, build a pre-processing pipeline, perform a stratified train/test split, and train a regularized logistic regression. Clean and reproducible. Option B reflects how production workflows are typically structured. The dataset is split three ways: training, validation, and test, each stratified to preserve class proportions. Hyperparameters and model choices are made on the validation set. The test set is held out completely and touched only once at the very end. But there is another rule that belongs here, discussed in Chapter 11. Always split the data before fitting any pre-processing. If scalars, encoders, or imputers are fit on the entire dataset first, information from the test set has already leaked into the training process. Even computing a global mean or standard deviation allows the model to indirectly see the test data. The correct workflow is simple. Split the data first, fit pre-processing only on the training set, and then apply those learned transformations to the validation and test sets. Why does this matter? Because if the test set influences any decision, through preprocessing, tuning, or repeated experimentation, it is no longer a true measure of real-world performance. The validation set absorbs those decisions, so the test set remains untouched. This is not just best practice. It is the honest way to evaluate whether a model will work when it leaves your hands. Chapter 2 of my book, Applied Machine Learning, Concepts, Tools, and Case Studies, covers all of this with working code, virtual environment setup, Git and DVC workflows, project structure templates, Pandas wrangling essentials, and the full bank marketing pipeline in both baseline and production-grade forms. If this is the foundation you want to build on, the link to my book is in the description. With a reproducible foundation in place, the next question is how to make your data as informative as possible before a model ever sees it. That means understanding which features actually matter and which ones the model should never be allowed to use. That is video 3. A model is only as trustworthy as the infrastructure it was built on. Get the environment right, version everything. Structure the project before you start. The algorithm comes later. See you in the next video.